Okay, hello. This is the continuation of the first few lectures on the basic principles of lasers. So I will start again with the date. It's March the 27th, 2020, and we are trying to be a bit, to improvise due to the lockdown. But anyway, I was discussing, I was trying to show you, and I mentioned the three requirements for having a laser, and also to create the laser phenomena. So the first requirement that I mentioned was a gain medium. The second requirement that I would like to use another color. The second requirement is a pump source. Yeah, and the third requirement is two reflective surfaces, which would create by themselves, even if they are not at 90 degrees angle, a cavity. So let me write them down again. I would say that it's gain medium, a pump source, and a cavity. The reflectivity of the surfaces might or may not be 100%. It's not a problem, but we can have, or we have to have at least one of them not 100% just to be able to have an output. And obviously our output would be, let's say that our output is in that way. It can be that way, or it can be this way, and it can even be in both ways. Is a laser beam which would have the characteristics that I just mentioned in the previous clip. I mentioned, without any importance on the order, I mentioned zero divergence, monochromaticity, and coherence. Yeah. So all beams are coherent, which means they are in phase. They say the divergence, in theory at least, is zero, and there is monochromaticity, which means that the laser emits only in one color. But of course, colors have spectrum, and there are some parameters to measure the spectrum in any source. So, but at the moment, I would like to explain a little how the laser process occurs in any case, in any type of laser. And basically, people, what they do is to use models, and the model that at the moment I'm going to try to use, or I'm going to use to explain this phenomena. It's a energy level model that was proposed initially for the matter by Niels Bohr, and then several other contributions, but Elias Nitzer in 1962, who created the first laser in semiconductors, proposed a three-level system. So, and obviously also please keep in mind that we are proposing, or we are going to focus into lasers made on fibers and with using as an active media as gain medium, rare earths. So the lanthanides and actinides in the periodical table. So let's start by stating that according to the levels of energy in matter, in any media, let's start with the first media that was studied in lasers, which was neodymium. So for the ground level with a population M0, we can assign an energy level of 0. Obviously, it's not true, but it's only theoretical. Then, for a population of N1, an energy level of 1, and for an energy level N2, with a population N2, an energy level of or an energy quantity of E3. E2. Anyway, So going or looking into the three requirements, this would be the gain medium. So this is an active material that has a spectrum of absorption and a spectrum of emission. So let's say that we are working on this, and then we have any pump source. Let's say a bright lamp which emits at the wavelength of which is coincident with the pump window or pump spectrum for the spectral absorption of neodymium. So we have the second requirement, which is a pump source, inciting or emitting the energy into neodymium. So what happens? According to Boltzmann population theory, the energy level or ground level in a stationary state has the higher population. Maybe I should also even write here a certain mathematical relation in initial conditions. Yeah. So in nature, the initial conditions is that the ground level has the highest population. So please imagine that the energy from the photons from the pump source, either photons, even could be electrical, chemical, but anyway, the energy going from, in this case, neodymium, the pump photons going into neodymium, whatever the form they are, either in fiber or in bulk, start pumping and providing the energy to the electrons in the ground level. So what would happen? What happens is that the material will start absorbing the energy that is provided by the pump source, and the phenomena is called absorption. Yeah? So you switch on your pump and the material is starting absorbing. After absorption at a certain level, then we can talk about population inversion. Let's say that we keep pumping with high power and in a continuous way over time, and then the population of N0 is much lower, is depleted, and then the higher energy levels have more population than the ground level. So that is called population inversion. Yeah. So we have population inversion. This is the second stage or the second condition or phenomena that occurs in this process. So after population inversion, we can argue, we can talk about in this system the gain and the losses are equal. At that time we talk about a point called threshold, and if we could we can draw a line of the output of this laser, we would be plotting power in in the system, which at the same time is the pump power. Yeah. And we would be talking about during the absorption stage and the population inversion stage, we would be talking about this sort of behavior. So there is absorption, there is population inversion, but still the power out of the output power of the laser is negligible. But at certain point, when the gain equals the losses of the cavity, then we talk about the point called threshold. At threshold, the material becomes transparent. If the material is transparent, then it is about to be ready to emit. But there are two options to emit for this material. When the ions are in the upper state levels and the high energy levels, they can by themselves release the energy. Yeah, they can release the energy, which means they go down in energy level, and they release the energy in a not organized or not chromatic, not monochromatic and non-coherent way. So there is a parameter called lifetime, on which the ions can be in the higher or upper level states. So lifetime is a parameter that governs how much time they can be in N1 or N2, and then they would emit. But as I said, there is no relation in lambda, in wavelength, and there is no relation in terms of coherence or monochromaticity for these photons. So they are photons, they are light, they are quanta of light, but there is no relationship between them, which it's called all by themselves. This phenomena is called, this stage of the phenomena is called amplified spontaneous emission. It's spontaneous, no other phenomena is related to them, and it's amplified because it's inside the gay media. Okay, so at that point, all the type of emission can happen on which both photons, or the two pairs of photons, and then the 4 photons, and the 8 photons, 16 photons, and all the cascaded photons have a direct relation in wavelength. Yeah, can happen. Yeah, and obviously within the spectra of emission of the material, and that is called laser. So it complies with the acronym LIGHT, which are photons, amplification by stimulated emission of radiation. Yeah, and the laser, or any photon, the energy of the photon of such laser can be calculated using this equation. Energy equals the Planck's constant multiplied by its frequency. The value of Planck's constant is already known, and we will continue next time just to explain how it would happen. But before we reach the point of threshold, and from amplified spontaneous emission, all the energy jumps into the same wavelength with monochromatic behavior. Yeah, and then we talk about an area or a region of operation where there is the phenomena that will occupy all our course. There is laser from the threshold point. Okay, thank you.